Greeting to everyone. I'm Peyman Behnam. It's my pleasure to present our recent work on STFL-DDR. This is joint work with my advisor, Professor Mahdi Nazm Bojnourdi. We know that last level cache and DRAM are major contributor to overall energy of multicores. Recent studies shows that interconnects are dominant source of energy consumption in LLC and also DRAM IOs. Scaling trends proves such high level of dynamic power consumption or DPC continues in the future. Several studies are trying to reduce the wire power. For example, leveraging low power wires, using techniques for improving dynamic power consumption based on the famous formula of alpha CV2F that mostly data encoding techniques, or using asymmetric termination, low voltage swing signaling, and also unterminated wires. The main reason is that termination circuit in DRAM interface dissipates a significant power or decrease voltage and frequency. Unfortunately, almost all of them constrain bandwidth and degrade performance. What is our solution to tackle this problem? Our solution is STFL, slow transition fast level signaling. What is the goal? Achieve a higher bandwidth in low power wires. Transition, for example, low to high switch on wire speed is the key bandwidth bottleneck in low power wire. Transition speed is a wire characteristic and hard to change. What is the key idea of our solution? Reduce the number of transitions per transfer data and signal the voltage level faster to reduce the transfer time. It's worthy to mention that STFL is the first architectural technique for hybrid signaling on cache interconnects and DRAM interface. What are the STFL design principles? Data encoding. STFL maps every one to a signal transition on the wire and every zero to the absence of wire transition. Transmitting signal. STFL sends the data bit at the same rate of a high performance wire, but there is a challenge. Signal deterioration is possible when transferring consecutive transitions. And what is the solution? Pause the transmission by injecting delay cycle after each transition. Receiving signal, STFL samples the low power wires at the high performance rate and removes the injected delays. What are the STFL benefits? So high speed wires need high voltage. That leads to high power consumption. On the other hand, low power wires lower voltage that leads to increased latency. STFL relies on low power wires and improves latency due to hybrid signaling. What are the STFL encoder-transmitter and decoder-receiver? Basically, how we can apply STFL in LLC. This is the hardware design. Transmitter. STFL reads the code bits serially from the shift register and converts them to the transition signal using a transition generator comprising a latch and also an XOR gate. A delay injector controls the shift register and maintains the previous output of the shift register. The delay injector is connected to the shift register via an active low shift signal. Every one transmitted in the previous cycle disable the shift register in the current cycle, thereby injecting a delay after every one in the code. What about the receiver? Every zero results in shifting the content and inserting the bit in a register. A 1, however, disables the shift operation and overrides the previously sampled value, which is dummy 0. How we can apply STFL to DRAM interface? So these figures shows the I/O power and the peak memory bandwidth provided by various DRAM generation, and also the proposed STFL-DDR mechanisms. As you can see, LPDDR interfaces consume a low power wire at the cost of limiting the memory bandwidth compared to DDR. However, STFL-DDR strikes a balance between power and also bandwidth. It employs low power wires from LPDDR3 to transfer data bits and high performance wire from DDR4 to carry the clock and also control signals. How we can apply STFL in DRAM I/O? This is the hardware design. STFL for the transmitter, STFL-DDR restricts the number of transfer ones per transmission to reduce the number of transition. First, a population counter computes the Hamming weight of each byte. If the result is greater than 4, the inverted data, otherwise the original data, is stored in a parallel in serial out shift register. This inversion is necessary to guarantee that no more than 4 ones will be transferred on data wires. Then the content of the shift register are serially read and converted into wire flips using a transition generator circuit consisting of a latch and also an XOR gate. Similarly to the STFL-LLC transmitter, a delay injector circuit controls the shift register by maintaining the previous output value and disabling the shift operation if the value is a 1. What about the receiver? The receiver comprises a transition detector and a serial in parallel out shift register. The transition detector employs an XOR gate and a flip-flop to convert every transition to a 1 and the absence of a transition to 0. The resultant bit stream is then sent to the shift register. STFL-DDR identifies and removes dummy zeros from the received stream simply by pausing the shift register and overwriting the previously received bit. Finally, the shift register content are XORed with the corresponding inversion bit to retrieve the original data. Here is the evaluation methodology. We used 3D-PK library, which is 45 nanometer. Then we scaled the result to 22 nanometers. We used SPICE model using PTM 22 nanometers. We use MacPad for processor power consumption, and we compare our work with different baselines such as DBI, BD, DESC, SET, and CAFO. In addition, we use different parallel benchmark. For system parameters, we heavily modified the ESESC simulator and set different parameters. For example, 4 cores, 32 kilobyte L1 cache, 4 megabyte L2 shared cache, and also the clocking circuit and pseudo open drains wires for mode bits or DDR4 at 1600 megahertz, and for data wires we use LPDDR3 at 800 megahertz. The right table also shows different parameters for DDR4 and LPDDR3. For example, VDDQ in both of them are 1.2. Energy per bit is 7.4 picojoule per bit for DDR4 and 2.6 for LPDDR3. Termination read and write power for DDR4 are 16.2 and 14. And of course, LPDDR3 is unterminated, so we don't have corresponding values for LPDDR3. And switching power for DDR4 is 3.4, and for LPDDR3 is 4.1. So what about the hardware overhead of STFL-LLC? STFL-LLC logic consumed less area compared to BD, CAFO, and DESC while incurring an acceptable delay and power overhead. What about the STFL-DDR hardware overhead? Same things, STFL-DDR logic consume less area compared to BD CAFO while incurring an acceptable delay and power overheads. So what about the total switching energy of STFL-LLC? STFL-LLC reduced the switching energy of LLC by an average of 60%. STFL-LLC savings are at least 10% better than those that gained by, for example, VFS, or voltage frequency scaling, disk, and sets with less hardware overhead. What about the CPU energy of STFL-LLC? STFL-LLC reduced the overall CPU energy by 27%. This is 1.2x of the average savings that obtained by voltage frequency scaling. And what about the performance? STFL-LLC alleviates the adverse performance impact by low power wires. For example, VFS encounters 6% performance loss. So for the CPU energy delay product, STFL-LLC achieved 9% better CPU energy delay product over VFS due to improving bandwidth and also reducing the switching energy. Here we study the switching energy when we have random patterns. STFL-LLC provides a superior energy saving due to low power wires and the proposed encoding mechanisms. For heavy blocks, where possibility of setting bits to 1 or row is greater than 0.8, VFS can save more switching energy than STFL due to encoding and also decoding overheads imposed by STFL-LLC. How about adapting STFL coding to data patterns? These figures shows the usage of each mode bit for all of the evaluated applications. The results indicate that most of the transferred data bytes have low Hamming weights and chose as the best code words to be sent. Now we study the results of DRAM interface. So on average, STFL-DDR achieves a 17% reduction in DRAM interface energy over LPDDR3. What about the DRAM energy? STFL-DDR reduced the overall DRAM energy by 26% in average. CAFO and BD encoding techniques achieve 18% and also 11% energy reduction respectively. LPDDR3 achieved an average of 22% energy reduction. The main reason for the marginal improvement of STFL-DDR over LPDDR3 is the fact that most of the evaluated applications can tolerate the bandwidth degradation imposed by LPDDR3. Here we show system performance of STFL-DDR. STFL provides almost the same performance as that of the high performance or HP DRAM interface. A delay in processing requests at the memory controller may result in a different schedule that may improve or worsen the system performance within a small margin. What about the system energy? Joint STFL-LLC and STFL-DDR improve the average system energy by 25%, whereas LP just saves only 19% of the system energy on average. When normalized to LP, STFL reduces the overall system energy by 8%. And what about the whole system performance? While LP incurs 10% increase in the overall execution time, joint STFL-LLC and STFL-DDR reduces the loss down to less than 2% and achieve 98% of the high performance binary encoding baselines. and system energy delay product join STFL-LLC and STFL-DDR improve the system energy delay product by 15% and 25% compared to the binary encoding on low power and also high performance wires respectively, due to improving both energy and also delay. In conclusion, I would say STFL is a hybrid technique for slow transition fast level signaling. STFL creates a balance between power and also bandwidth in the last level cache interface and also DRAM interfaces. STFL holds the promise to help the system designers build energy efficient computing system. Please refer to our paper for more details. If you have questions, feel free to send us emails. Thank you so much.